Here. Okay, so the five types we have: synthesis. What else? Decomposition, single replacement, and the hard one, combustion. Hey, you know what? I think I'm going to do on that part too. Then I have about 12 of them, maybe 12, where I write the whole thing out, and all you do is balance it. I said, well, I'm pretty good at balancing equations. You know, you showed me some of those tricks, and even that combustion one, I remember that. You know, don't put an odd number in front of water if it's combustion, right? Double it. So anyway, so you have some of those, and then we start. Part of it has to do with this, where you have word equations, and you have to change the word equation into a balanced equation. So you're saying we did all these? So you're pretty good at this? Okay, so what do we have to be careful about here? We had, in one case, look at this right here. This one could be a difficult one. And is it true that if you thought, oh, I'm not good at writing formulas, but it doesn't matter. If that's what you thought wrong. Okay? I told you that before, and that's why I even gave you a retest. I said it's really important to be able to write formulas. So here we have aluminum bromide, and we know aluminum's +3 and bromine's -1. And so, okay on that? Okay, see how you're using the law of skills? And then, what are you going to add to it? Chlorine. Wait, a little bell went off in my head. Why did a little bell go off in my head? Chlorine. The element chlorine. What do you think? It's one of the diatomic elements, isn't it? Right? See, I can have as many bromines as I want in a compound, but if it's just the element bromine, it's diatomic on this earth. Yields aluminum chloride. Okay, aluminum is always +3. Okay, just a coincidence. Okay, and then what else is this? Bromine. Okay. Ever got it? So you do not ever try to balance an equation. By the way, what kind of numbers are you going to use to balance an equation? Coefficients. These are not, when I write this, I'm not called balancing. I'm writing a formula. Get that? But here, when I balance an equation, I use coefficients, and I scan through here, and I look for odd, even mismatches. Here's an odd, even mismatch right here. Here's an odd, even mismatch here. Here's 2. Here's 3. I'll put a 3 here, a 2 here. That gives me 6 bromines. 6 bromines, 2 aluminums, but that gives me 6 chlorines. What do you think about that? So what do you think about that part? Even if it is the word equations, there's just a few things. I have to remember diatomic elements. I have to know how to write formulas, right? How about acids? Maybe you need to look back and take a 5-minute review of how do you name acids. Everybody got that? All right. And I think you can be ready for that. All right. We also, the last thing I want to talk about is today, as I do my demonstrations, I would like you to ask yourself, why did that reaction take place? What is it that drove the reaction to take place? Because I could put some copper in some hydrochloric acid, and guess what's going to happen? NR, no reaction. What? If I put copper in hydrochloric acid, nothing's going to happen. That's right. You can't do a balanced equation. It doesn't happen. But what about this? This is one you're going to do. This is a lab you're going to do later. You're going to put zinc in hydrochloric acid, and you will get bubbles. And you'll test those bubbles, and you'll test and say, what is that? That's hydrogen. It's explosive. You're going to have a little mini explosion in a test tube. And then what else is made? Why don't you help me with that? Help me with this one. What kind of reaction? How do you classify that reaction right there? Somebody said it. Okay, so tell me what I'm going to put here. Zinc what? And how do you write zinc chloride? Everybody got that? Now let's balance it. What do you think? Okay, this is trying to get you to that next level in chemistry, right? That's where we're at. All right, so we have these driving forces, and this one was the formation of a what? I put a little G here, right? The formation of a gas. So as you see the demonstrations today, I think you'll say, I'm not so afraid. I'm not afraid of those word equations. I should be able to do the word equations. All right, any questions on the test? I am going to put pressure on you. Honestly, this test is not that much material. It's not that much material, you get it? If you practice balancing equations, you get that? And you figured out some of the tricks, and you know your vocabulary words, and you know how to classify, well, you're in pretty good shape. And I am going to put pressure on you. I do believe you can score very high on this test. You have to believe it, though, don't you? You have to believe it. Okay, yes?
So I know we didn't do this, but in number 4 and number 5, different products are it's hydrogen and oxygen gas. Do we need to put the symbol for gas?
Okay. Next chapter, we actually will do a little more of that. I may ask you on this test to do it maybe a couple times. I might have, maybe I did. There might be 2 of them that I make you write the symbols also, okay? Now, I'll tell you what, I may have to wait till next chapter because you need some other tools. There's some other tools I'm going to give you where you look in a chart and you say, and I can teach you a little bit more, okay? So if I did, it would be something simple like the one I may not do this today because I did it the other day. Do you remember how I took a battery? Remember I took a 9-volt battery one day and I put it in some water? And so let me just go ahead and do number 7 first, where in your mind. I took H2O and it was a liquid, so I'll put an L there. And then I put some electricity, didn't I? and I actually added a little bit of salt in there, and the salt wasn't going to do anything except it wasn't a reactant, it wasn't a product, but I put a little salt in there because I needed something to help me move the electricity through it. So I needed some ions to move the electricity through the water. So if I take some water and put a 9-volt battery in it and add a little bit of salt, I'm going to get 2 kinds of bubbles. I'm going to get hydrogen gas and oxygen gas. I'll put a little G here. So I think there's a great question, Caroline. More next chapter. More next chapter when I show you some things. All right. Well, let me go ahead and let's do the first one. And I think they'll like this one. This one is I'm going to take some chemicals here. Here's one, and oops, where's the other? Oh, here's the other one. And here's this, and one more. There you go. All right, so here we go. This one is going to be. Can anybody help me translate this a little bit? Somebody volunteer and translate this for me. Jonathan, I didn't call on you yesterday. Could you translate that for me? What does that say? And what am I going to add to it? Right. And by the way, this is a very classic acid, right? And it's a liquid. AQ means acids and bases are always dissolved in water. So that's AQ. And this NaOH, AQ, it looks like water. Okay, so here we go. Now what I'm going to do is we're going to add some, I'll start with this. Let's start with this. Actually, it doesn't matter which order I pick it in. So let's put a little bit, there we go. So that's NaOH, aqueous, and what does it look like? It's water, doesn't it? It looks like water, but you said, I don't believe it. I don't believe you really have NaOH in there. Really? Okay, well, let's see. And then I'm going to put some HCl in there, and you say, well, what does that look like? What does hydrochloric acid look like? And I'll put that over here. Uh-oh, dang, they missed. Okay, they mixed. What happened? Wow, that was exciting. That was really exciting. Do you believe that I actually did mix those two? Okay, let's go ahead and classify it. Would you classify that? And how would you classify this right here? Elizabeth, you're pretty good at this. You're right. So if it is double replacement, tell me the two products. So it is double replacement. HOH, also known as what? Okay. And what else? And is it NaCl just like that? Say it again. Try it again.
No, just NaCl.
That's it. Yeah, because this is +1, this is -1, isn't it? Now, now we need to balance it. Go ahead and balance it. Let's see who's the fastest one to balance it. Go. Too slow. All right, what are you required to do on the test tomorrow if it's already balanced? Isn't that right? You have to write balance, isn't it? Because look, there was one sodium, one hydrogen, not in hydroxide. Okay. Anyway, so that was already balanced, isn't it? Now, Mike, you said, why did you even do this? Because it was kind of boring, wasn't it? Well, I have a little helper here. And we had some helpers at the beginning of the year. Remember these, what do you call chemicals that show you something's going on when it doesn't, you wouldn't be able to tell normally? It starts with I. What do you call that group of chemicals that can change color and they let us know that something's going on? What is it? Indicators. Okay, now I have a new indicator for you, okay? And this new indicator is, I might put that as an extra credit. Oh, that'd be a good extra credit on the test tomorrow. How do you spell phenolphthalein? Phenol. Now watch this. PHTH. What? PHTH. I've never seen that. And then AL. And then you think you're done because a lot of words in the United States are IE, but not this one. EI. Oh, man. That'd be a good one. So let's take a look at phenolphthalein, okay? And I think I didn't want them in the mix right away, but they did, so I'm going to start over. Oh, you want it in the mix. There you go. So what I'm going to do here is, let's put some HCl over here. Doop, 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 doop. And let's put some sodium hydroxide over here. Doop, doop, doop. Okay. By the way, I made a mistake here. All right, here's my little buddy. Phenolphthalein. Phenolphthalein, what do you look like? Phenolphthalein, what do you look like? What's it look like? Water, okay. Phenolphthalein, when are you going to do something? Well, add me to acid, see what happens. Okay. What happens to phenolphthalein when I add it to an acid? Nothing. This is boring. Add it to a base. Oh, I see. So when does phenolphthalein, see BTB had 3 colors, didn't it? Didn't it have blue, green, and yellow? Well, how many colors does phenolphthalein have? 2. It's either clear or magenta or pink, whatever you like to say, okay? What do you think about that? When does phenolphthalein change pink? Yes?
I don't have that sheet.
Oh, I think you're fixing your water bottle. Go back to that last table. Sorry. All right, so here we have, and this is going to be important because phenolphthalein will only change in the presence of a base. Now, what is a base? And a base is a metal hydroxide. Now, this is sodium hydroxide, right? So that's a base. Everybody get it? So it'll turn pink in the presence of a base. Now, I want to show you something here. Right now, the indicator is saying that's a base. That's not, but that's a base. Okay, so I'm going to add some acid to the base. Now, what happened to my color? And here's this little game they're playing, okay? There's an ion in acid. There's an ion in acid called the hydrogen ion, and that's why acids always start with H, because he's very, very important. There's another ion in a base called hydroxide. See that? And there's a little game we play. What if you have more H's than OH's, then you're going to be an acid. What if you have more OH's than H, you're going to be a base. And what if you have the same number, you're going to be neutral. Neutral pH, you get that? Acid, neutral, base. What is it now? It's either neutral or what? Or an acid. So can I bring the pink color back? Can I add some more base down here? Who's winning? Now acid's still winning. Who's winning? Who's winning? Who's winning? Oh my gosh, that acid was too concentrated. Okay, I think my acid was way too concentrated. Come on, who's winning? Come on. All right, now who's winning? All right, now the base is winning. It's a neat little game. Go to college, become a science teacher, and you can do the same thing. All right, now who's going to win? Let's put some acid in here. Oink. All right, now who's winning? Wait a minute. So the phenolphthalein does not go away, does it? It's not going away. It just tells me what's going on, whether or not is there more acid or is there more base or neutral. So phenolphthalein, when it's neutral, is clear. When it's in an acid, is clear. But it only changes when it's in a base. Okay, you'll have to remember that. Okay, so number one, what do you think about number one? It was a double replacement, wasn't it? And we balanced. It was already balanced, so I wrote balanced. And we learned about a new indicator called phenolphthalein. And we now know that acids have this ion and bases have this ion. Okay. All right, let's do the next one. The next one, I'll tell you what, I'm gonna wait and do that last. Let's do the next one. Let's go down to number 4. Let's go down to number 4. Okay. And by the way, what was the driving? Oh, I forgot to ask you. What was the driving force for number 1? Why is it you think that reaction took place? What was the driving force? Anybody? We gotta get going here, okay? Formation of water. See it right there? The formation of water, okay? And that was actually the driving force. Let's go down to the next one where it's different. Number 4 says the formation of a solid. So what I'm going to do here says, is anybody, let's see, I'm going to pick Danielle. Ready? Can you read this to me in English? That's NO3.
Silver nitrate plus calcium
It's an always metal, so you don't have to worry about Roman numerals.
calcium chloride.
Yes. And both of these are aqueous solutions, aren't they? Let's go ahead and get those out. All right, here we go. That's not you. That's not you. There you go. Okay, so guess what? What does silver nitrate look like? What does silver nitrate aqueous look like? Here we go. Ooh, exciting. What does silver nitrate aqueous look like? Water. It's dissolved in water, isn't it? And what does calcium chloride aqueous look like? What do you think? Wow, this is an exciting day. Okay, so what I want to do now is, what I would like to do is, I haven't actually mixed them together, have I? I have not allowed them to react yet. So what's going to happen here, we're going to get a reaction. I need to do something here. Hang on. I forgot. I need a dark piece of paper. Okay. That's not dark. Okay, I'll try it. I was going to try to move it, but I'm afraid they're going to mix together. Let me go ahead and mix them, and let's see what happens, okay? All right, right now, nothing's happening. Let's go ahead and mix them. Boing. Okay, now watch. Let me get rid of the white background. All right, so what happened? What happened? That doesn't look like water now. It looks like milk, doesn't it? And what you have here, I'll shake it a little bit here, and you'll see, if you let this sit for a while, you'll see that those are little tiny pieces of solid. So we actually have made a solid. We started out with things that didn't look like a solid, and now we have a solid. And so let's go ahead and see if we can figure out what that solid stuff is. What is that stuff? All right, so let's go with, let's go. Hey, Max, help me out with this, all right? Max, what if you had to guess what type, you don't have to guess, never mind. It's double replacement. Tell me what am I right on the right-hand side of the arrow? Ooh. Right. And this is very much like a question on the test. I tell you this double replacement. Can you write the the products and balance it. All right, go.
Let's see, so
Say it again.
would be silver, fluoride,
And how do you write that?
silver, and then fluoride 3,
3. Okay, why do you say 3?
because it's -1.
Okay, so what is? What's -1?
Chlorine.
Okay, I agree. This is -1, but what's silver?
Oh, it's +1.
Yes, okay, everybody got that? So silver is +1 and chlorine's -1. Now, do not fall into that trap thinking, hey, double replacement, I'll just put the Ag next to Cl2. We had a whole chapter on how to write formulas, and you do not write silver chloride AgCl2, do you? What you do know is silver will form a compound with chlorine the same way he did on that other chapter. And so +1, -1, we're done. And why does that say gas? That's a misprint. That's S. I don't know. Somebody typed it. That's my fault, but I should have caught that. Anyway, so what happened is the thing that we made here was actually a solid. And next chapter, I'll actually show you on a chart how do you know which one of these products is a solid, okay? And what's the second one, Max? You did a great job on that. What's the next one?
Would be calcium nitrate.
All right, how do you write that?
This
Look on a periodic table. What's the charge on calcium?
it's +2.
Yeah, and what about nitrate?
To -1.
All right, so what are you going to do about that?
2 nitrates.
Yes. Okay, and again, I'm not going to ask you which one is which on the test. I wouldn't. You're not supposed to know yet which one is a solid, which one. But it happens. This is the most famous white precipitate in chemistry called silver chloride, and you don't have to know that. But now let's go ahead and balance it. Ready? Go. Balance it. Go. Scan, scan, scan. Nitrate stays as nitrate. 2 nitrates. 2 nitrates. 2 silver. That gives me 2 chlorines. Okay. What do you think? Not bad? Are you just playing with me? Is your face telling me you really understand this, or you get... Okay. All right, is that all right? Okay, let's do that one. Let's do another one where the driving force is formation of solid. Let me put this one up. There's that. Let's put that one up. Okay, I need, let's have Caroline Kubert. Why don't you read this to me? I need to translate the English into Khmeris. Real loud, a little bit louder. I wouldn't look on the periodic table for nitrate. And what's the charge on? Okay, so lead's +2, isn't it? So what are you going to do about that? All right, so lead 2 nitrate reacts with what? How do you do that? Any subscripts? Right, this is +1, this is -1, isn't it? Okay, now, in the test, I probably, okay, so now what I would do is, we need to finish this. So it is a double replacement reaction, so you did very well so far. You want to continue this? Can you do it? Okay, go ahead. What's going to be formed here?
I don't know which one is the solid and which one's the...
Okay, that's fine. Don't worry about that.
So, lead, iodine...
And which lead? And again, since it's first year chemistry, I'm not going to, if it started at lead 2, it's going to end with lead 2, okay?
So, PbI2.
So lead 2, iodide, but iodide is -1. So how are you going to write it?
2.
Okay, everybody get that? That has nothing to do with iodine being diatomic. That just happened to be, that's how you write the formula, right? Now keep going.
And then sodium nitrate.
How do you write that? You keep looking at the periodic table for nitrate, but it's not going to be there.
I'm looking at it.
Oh, for sodium?
Yeah,
Okay.
nitrates NO3.
What's nitrate?
NO3.
What's the charge on nitrate?
-1.
So we're done. Okay, let's balance it. Ready? Go. Balance it. Okay, as I scan through here, I notice 2 nitrates, 1 nitrate. I can fix that. That's 2 sodiums, 1 sodium. 2 iodines, 2 iodines. What do you think about that? Now, can it be reduced? You always check, see if it can be reduced, right? Okay, let's go ahead and do that one. This one is one you're going to do later in a lab. There's a lab you're going to be doing. And except instead of just putting it on a dropper, you're going to do, we'll get into this thing called stoichiometry. Stoichiometry is where you do mathematics. And you'll have so many grams of one chemical, and you're going to combine it with so many grams of another, and try to figure out how many grams of product. So that's where we get to the math. That's in second semester, all right? So here's lead 2 nitrate. Be careful. So this is just an exciting, really exciting. Okay, everybody see that? What's that look like? Okay. So lead 2 nitrate aqueous looks like water, doesn't it? And what's the other chemical? Sodium iodide aqueous. Oh, look out. What's that look like? Okay. So now what? You want to put them together? Okay, let's let them react. Careful, watch now. Get over there. Get over there. Get over there. What's that? Ooh, that's pretty neat. And again, if I let this sit for a while, as a matter of fact, if I let it dry out overnight, you'll see the solid. The solid will still be left behind, and there is a solid in there. It looks like mustard, doesn't it? But it's actually a solid in there. That's why you can't see through it anymore. You see, you can't see the letters anymore? You can't see it through it because they're solid. It's little grains of this chemical. And next chapter, I will show you how you know which one it was. And you're right, you wouldn't know this chapter. You wouldn't know which one the solid was, okay? All right. Come on, there you go. What? I've never seen that before. All right, what do you think? What do you think so far? So is it that hard to take English words and turn them into Chemonese now? Can we do that? We're getting better at it? Okay, let's do, is that there? The next one I'm going to do is, all right, this one, I'm going to go all the way down to number 6. Let's go all the way down to number 6, okay? And here's what I'm going to do here. This right here is the element called magnesium. Now, you can buy magnesium lots of different ways. I could buy magnesium powder. I could buy magnesium granules. Looks like sand. But I can also buy magnesium ribbon. What do you think magnesium ribbon is made of? What do you think magnesium pellets are made of? Okay, hang on. That's an easy question. What do you think aluminum foil is made of? Everybody in my class knows that. What is it? It's aluminum. Why do you call aluminum foil? Because it's in the shape of foil, like paper. You get it? Can you buy aluminum pellets? Yes. Can I buy aluminum bars? Yeah. Can I buy aluminum ribbon? Yeah. So when I say I have magnesium ribbon, all that means is that this is magnesium, but it's in the shape of a ribbon. It's like real thin strips like that. So what I'm going to do here is, tweezers. You see tweezers? Okay, they're there. I'll use these. Let's use these. I have some tweezers here. No, yeah, I know I did. They're there. All right, now this one is interesting because you can buy magnesium. As a matter of fact, companies take powdered magnesium and put it on things like fuses. Like if I had a fuse and I coated the fuse with magnesium, you could actually light it and throw it in the water. It would stay lit. Because the heat produced by this is so tremendous that even in the water, the water would never be able to get to the fuse itself, and it would just stay lit. So what I'm going to do is I'm going to light this. You guys are very close to starting the lab where we actually do use the burners. And this burner here, okay, can everybody see that? That's pretty hot. And I'll teach you all about safety and all that kind of thing. Now I'll try to be as safe as I can. What I'm going to do is I'm going to burn the magnesium. What does that mean, burn? What does it mean in chemistry? Combined with what? Oxygen. That's what I'm going to do. Where am I going to get the oxygen from? How about right here? Okay. Ready? Now, I'm going to caution you. When the light is so brilliant that you're not really supposed to stare at it, because not only does it have regular white light, it also has a certain amount of ultraviolet. So I don't mind. I'm going to have you turn off those lights and those lights. Turn off both of those. I'll show you how bright this is. This tiny little piece of magnesium. See it? All right. Thank you very much. Everybody ready? All right. Please don't stare at this. Okay. If you want to look at the screen, you can. But it is going to be incredibly bright. Everybody see that? Okay. Now, we'll just leave the lights off right now. All right, so what I have here is, do you notice any evidence? Do you see any evidence that maybe a chemical reaction took place? What do you think? Like, I still see a little bit of magnesium here, don't I? See that? There it is. Look. There's some magnesium here. What's that white powder? Oh, that's interesting. Do you think the white powder is magnesium? So let's take a look at this, and I'll show you. We're going to do some more with that. Go up to your sheet, number 6, and what do you think's happening there? Okay. Oops. Hang on. Let's see here. Let me go here. Let's go ahead and write that out. It says here, energy release is another driving force. Some reactions release energy. That's a driving force. But this is definitely evidence of a chemical reaction. We had a lot of energy given off, a lot of light energy, and as a matter of fact, a certain amount of heat. So magnesium was burned by combining with oxygen in a synthesis reaction. Go ahead and write that down. What do you think was formed? What do you think was formed here? All right, everybody got it? Let's see. Ty, what do you think? What do you think the product is going to be? It's a synthesis reaction.
I said MgO.
Say it again?
MgO.
And Mg is +2 and oxygen is -2. So you think that magnesium oxide is formed? I agree. Very, very, very good. Now, let's take a look here. Magnesium oxide is like this white powder, isn't it? Now, what I'm going to do is I'm going to do another reaction. I'm going to do a piggyback reaction. I'm going to add some water. I'm going to take the product of this reaction and make it into the reactant of a next one. Okay, now, I don't think you're going to be able to tell me what's going to form here. So what I'm going to do is I'm going to add some water to this and see if a reaction takes place. All right, so let me get some water here. Okay, so here's some water, and what I'm going to do is put some water on that white powder. Now, again, that's not really exciting. That's not really exciting, but right now I know that that the water and the magnesium oxide there's something going on. And you say, how do you know? How do you know something's going on? And I'm gonna give you a little hint here, okay? I'm gonna take my little buddy, phenolphthalein. And let's see what happens if I put some phenolphthalein on here. Okay, what happened? What do you think? Help me out. Put the pieces of the puzzle together here. What do you think is formed here? Raise your hand if you think you know what was formed when magnesium oxide reacts with water. Anybody else that had? All right, Carolyn, what do you think?
Magnesium oxide.
Magnesium oxide was formed in the original reaction, but then I let magnesium oxide form. What did you say it was? Magnesium what? That is magnesium oxide.
Oh, sorry.
But when does phenolphthalein change? Yeah, Ty. Yes, in a metal hydroxide, right? So I believe that magnesium hydroxide was formed. Can everybody write that down? Write down the formula for magnesium hydroxide. See if you can do it without any help. What's the formula for magnesium hydroxide? All right, hopefully you knew that magnesium was +2 and hydroxide is -1. Hopefully you wrote this right here. Did you? Okay, now if this was a synthesis reaction, what was this one? How would you classify this piggyback reaction? Now again, most of the test is not this. You understand that? Most of the test is not this. But what do you think? Caroline Fox, what do you think? How would you classify the second reaction here? And I'll give you a clue. A clue, whenever I see water on one side of the equation and hydroxide on the other, I'm going to write this as HOH. And I think that might make it easier for you. How would you classify this reaction? Okay, that's fine. Now, do you see that what happened here? Do you see the metal, magnesium? And instead of forming a compound with oxygen, it formed a compound with what? OH? So the magnesium must have kicked the what out? What did the magnesium kick out? Hydrogen, right? It kicked hydrogen out. And so hydrogen's over here. And then, it kicked HOH. Wait a minute. Right, okay, sorry. That'd be H2. And then this right here it formed a compound with hydroxide, made magnesium hydroxide there. Now right now, I guess I didn't look close enough there. This suggests that some hydrogen gas was produced. I didn't see it, but it could have been there. I would have had to look a little carefully. But I do have the last two reactions. The hydrogen being produced is going to be very evident. And as a matter of fact, it's going to be violent. So I saved the last two for the last. All right, so let's put this over here. And let's move this back here. And what I'm going to show you now is if you were to go on the internet, they have many, many very thrilling reactions on the internet. And some of those are really, really dangerous. I'm going to do the ones that aren't too dangerous. But they have people there willing to go on YouTube and show you some really dangerous reactions. If you take a look at the periodic table, not only are these metals, but when you go left, as you go left on the periodic table, the metals become more chemically active. That means that they really like to react. And so if you go to the left here, what group of metals are the most reactive metals on the periodic table? They're called the alkali metals, aren't they? Here's another trend. Not only when you go left do the metals tend to get more active, but as you go down the periodic table, they become more active. So what I'm going to do is, I'm going to show you, I don't have lithium, but I do have sodium. I'm going to have that react with something. And then I'm going to show you potassium, which is going to be even more reactive, and I'm going to stop there. I could ask the school to have me buy some rubidium or cesium. Number one, it would be kind of expensive, but it would also be very dangerous. So if you have time to look on YouTube, I don't think I'll have time today, but if you have time to look, and maybe after the test I'll do it, but if you look on YouTube, you'll see people who actually get in a bunker and they put a big piece of like cesium in a bathtub of water and then they go far away, and it's a huge explosion. It's very dangerous. So I'm going to do the ones that should not put you in danger, okay? So let me show you something you'll probably never see in the real world. You can see it on YouTube, but you'll never see it in the real world. I did ask the school to buy this. And so it actually costs a little bit extra to even have this sent because of it's called a hazardous material. Until before 9/11, even you could order some pieces of sodium and they probably sent it to your house. But after 9/11, they just stopped doing lots of things. I got that? And so I can get this because it comes to the school, and the school has a license, and so I can get this, but you can't get it. This is actually a kind of dangerous material. Sodium is so reactive that when they send it to me, they have it in oil. It's actually sitting in oil because it'll violently react with water. So I don't want it to come in contact with water until I want it to, right? And why do you find gold mines out there and silver mines and copper mines, but you don't see sodium mines? Why don't we go dig sodium out of the ground? It's because it's so reactive. Matter of fact, if I take a piece out of here, and I'll show it to you on the camera, just in about 3 or 4 seconds, it'll combine with oxygen in the air and make sodium oxide. So let's see if I can show this to you. All right. Now, say if you said to yourself, I've never seen sodium, I'll show you what it looks like. There it is. Now, can everybody see that? I'll tell you what I'm going to do. Let me get rid of the white background. Everybody see that? Okay, so let me show you something about sodium. All the alkali metals have certain things in common. Number one, they all violently react with water. Number two, almost all of them are soft metals. Watch, I'm going to take a little spatula, and it's kind of like hard butter. If you ask me, you can cut this metal with just a little piece of spatula? Yeah. Okay, I can do that. Now what I'm going to do is, this piece here is too dangerous. And this piece here, I don't like that one either. That's pretty dangerous. So I'm going to cut that in half. Now, again, do you notice that, go back in there, okay? I know it doesn't look dangerous, does it? All right, but I'm going to put this in water. So what I'm going to do is, let me pick this up, put some water in there, and then we'll put it back in there again. Okay, so let me try it again. Here's some water, okay? Can everybody see it? Okay, now, what do you think is going to happen here? Let's take a look. Can you hear that sizzling noise? Like bacon? Oh, fire! Okay, now, this is actually a small piece. And that could be dangerous, but a big piece, it can be very dangerous. So I want to ask you something. I'm going to give you one more clue here, and I want you to tell me if you think you can figure this one out. Here's my little buddy again. Buddy. Everybody see that? All right, so whoever you're sitting closest to, see if you can figure out reaction number 2. And what is sodium? Oh, did I give the answer away? I guess I did. What happens when you react sodium with water? And how did I know that sodium hydroxide was one of the products? What do you think? Noah, what do you think? How did I know that sodium hydroxide was going to be one of the products? And you can just say, I don't know. Okay, did you see the phenolphthalein change? When does phenolphthalein change to pink color? And is sodium hydroxide a base? Is a metal hydroxide a base? It is. It is. So metal hydroxide up here, we had sodium hydroxide up here, didn't we? So the only reason you would know that sodium hydroxide was made was phenolphthalein. Without the phenolphthalein, you would not know. But there was something else that happened. there was bubbles. Lots and lots of bubbles were given off. And what do you think that was? So let's help me out here. I see hydroxide on one side, and I see water on the other. So I'm going to write water as HOH. Let me ask John. John, what do you think? What kind of reaction do you think this is? Yes. So the sodium kicks out the hydrogen and forms a compound with OH, doesn't it? And so where's the hydrogen at? And why did I write H2? It's a diatomic element, isn't it? Now let's go ahead and balance this. 2 hydrogens, not in, okay. Put a 2 there. That's 2 hydroxides, 2 sodiums. Okay. Now, can anybody in here tell me why in the world I saw fire? Why did I see fire? What was that all about? Sometimes, many chemical reactions, when you react things, they give off energy. A few reactions take in energy, but most of them will give off energy. But there must have been a lot of energy released here because something caught on fire. Which one of these things maybe you don't know that, but one of these is very flammable material. Does anybody know which one is flammable? Is NaOH flammable or hydrogen? Hydrogen. It's very, very flammable. Anyway, so what happened is there was actually another reaction that took place. It's hard. Do you know the other reaction that took place? Hydrogen gas combined with something. Does anybody know? It was burning. Oxygen, right. And guess what it formed? It formed water. And got some more water there, okay? And I needed some kind of energy source, so we had enough heat there. Anyway, so that's a fairly violent reaction because that was a pretty small piece there. So you want to jack it up one? You want to go up one level? Let's go up a level. And this will be our last one. Let's go up one more level. This guy back, sodium. Let's go down the ladder, which is going to increase it. So, and again, I did not ask the school to buy anything more dangerous than potassium, but this is pretty dangerous. Again, if I had a piece bigger than the one you saw, I would be putting myself in a little danger. And if you have a lot of hydrogen gas and it all ignites at the same time, you can get a pretty good explosion. And I don't want that. I'd rather not have that right now. All right, so let's take a look at a piece of potassium. Potassium metal. Again, stored in oil. Oh my gosh, that's dangerous. Ooh, that'd be bad. Okay, I'm going to show you again, though, that like all alkali metals, it's pretty soft. Pretty easy to chop off there. I don't know if you can see that very well. Probably not. But if I make a fresh cut, it's going to be very, very shiny, like silvery. But within about 2 or 3 seconds, it'll go gloss over to kind of a dull gray, and it's actually combining with the oxygen in the air. That's why you don't find sodium mines, because sodium's so reactive. It'll react with water. It'll react with oxygen, and so you don't find that. So I really don't want to have a big piece here. Okay, maybe. All right, let me get ready. That's pretty big. All right. The good news, nobody sits real close, so I think I should be all right. Okay. Let's do this. Okay, you stay there. Okay. Is there some water? Oh, I think I had a little piece in there, didn't I? Whew, that was a tiny piece. Whew, ready? This is going to be a little more violent. Wow. I mean, that was a tiny, tiny piece, but it violently reacts with water. And if like I said, if I were to have a piece of rubidium, it might produce so much heat, it could even crack. It might even crack that bowl. And if I had cesium, it would probably produce and explode the hydrogen so quickly, it would explode. And a glass would go all over the place like that. Now, the good news is I must have had a little bit of phenolphthalein left in there from my other experiment, and so it also turned pink. Can everybody see it turning pink a little bit? I'll put a little bit more in there just so you see it. There you go. All right, so let's try this one. All right, everybody, this is the last thing you have to do today. If you can write out the formula. I think you're going to do well tomorrow on the test. By the way, if you still don't know your polyatomic ions or you still don't know how to write formulas, that's what I spend most of my time on, okay? All right, so everybody have the last one done? Did everybody get that one done, you think? All right, again, I want to mention one more time. It's only a little more than maybe 10% of the test is what you're seeing here. Maybe 15 at the very, very, very most. The other stuff you've already know pretty well. So as far as changing word equations and that kind of stuff, maybe that's not a huge part of the test. It's not like 30 or 40% of the test. It's like 10%. All right, well, have a good day. And I will be here. We have a meeting after school today, but I'll be here at lunch. If any of you need any extra help, I could do that. Even though I have car duty tomorrow, if you were to ask me between 8 and 8:15, I might be able to help you a little bit there also.
For these, how are you supposed to know that these things are a product?
Which ones? What do you mean?
Well, just for these two in general, like how would you know that that was a product?
Oh,
without you
okay.
giving it to
So
us?
what I would do is, on a test, I would have to tell you it was single replacement.
Oh, and then we could just do it.
Right. So what I did is I did phenolphthalein, and phenolphthalein told me that you probably have a metal hydroxide. So that gave you the clue that you probably have potassium hydroxide. And then you would guess, I think it must be a single replacement reaction. But on the test, I might have something like, in a single replacement reaction, potassium reacts with water. And if you say single replacement, that's HOH, right?
Oh, okay, so if you just give us, like, if you didn't give us this, you would tell us it was single
Yes,
replacement. Okay.
In this case, the phenolphthalein told me one of the products was probably potassium hydroxide.
Okay.
But that's a little bit harder than the test.
Early tomorrow morning if you have to.
If it's real early, I have at 20 tills when I have car duty. So if you want to come, I get here around 10 after 7, 15 after maybe. If you want to go from like 7:15, 7:20 to 7:40,
Yeah.
I could do that.
Okay, sounds good.
And when do you have this class tomorrow? What time? Is it
I think
after
that's
lunch?
our last class tomorrow.
Okay, so I'll be here. Well, no, I had lunch with you. Sorry,
Yeah.
I do have lunch.
Okay.
Okay. Oops,